Hi all. Today we're going to talk about something a bit different as we will see an application of word embeddings, and we will take this as an opportunity to explore the world of graph neural networks and graph embeddings. In fact, the idea of creating continuous vector representations of object of interest and using these representations to better perform some downstream tasks is something that is not limited to the natural language processing world, but it is very common, I would say, especially in the deep learning domain. And one particular area that has received a lot of attention lately and that is currently one of the hot topics of the deep learning community is that of graph neural networks. Graph structured data has in fact been largely neglected by the machine learning community, and just around 3 years ago, the first graph neural networks were introduced, and these neural networks were capable of working with graph structured data, and they are now, as I said, one of the hot topics of the deep learning community, and they are already the state of the art of many graph related tasks. So this is the outline of what I will talk about today. I will start by giving a very brief introduction to graph embeddings. I will give a very brief presentation of the past approaches, and then I will get into graph neural networks, and we will see the general message passing framework. We will see graph convolutional networks, graph sage, which are two very popular models. And then just as a curiosity, I will present a few real world use cases. And finally, we will talk about the paper that we will discuss in the next group meeting. This paper merges uh, graph neural networks and word embeddings in order to create a model that is capable of performing the textual entailment task, which I believe is really, really cool. So I'll start by introducing some notation. First of all, we will deal with graphs where each node has a feature vector associated with it. And if a network doesn't have feature vectors associated to its nodes, then you can simply create these feature vectors by assigning them to random values or using features such as node degrees or node centrality or something like that. So we will embed the graph in a tuple composed of two matrices. The first one is the adjacency matrix. So it's the classic matrix that I think we all know about, where the element at the ith row and jth column is equal to 1 if the ith node and the jth node are connected together in the graph, and 0 otherwise. And we will also define the adjacency matrix with added self loops. We will then define the degree matrix, D, which is a diagonal matrix, where the ith element of the diagonal is just the degree of the ith node. And very similarly, will define also the degree matrix for the adjacency matrix with added self loops. And finally, the matrix X will be our feature matrix. This means that the ith row of the matrix X will be the d-dimensional feature vector of the ith node. So the idea of graph embeddings is to assign a meaningful vector representation by each node. And by meaningful, I mean that it is useful for downstream tasks. So this is a very classic graph, the Karate Club graph. And we have that here. Each node is assigned a color based on a spectral clustering. And we have here a two-dimensional vector representation of each node that preserves this clustering. The main applications of graph embeddings and the ones that you will see the most in literature, if you're interested, are node classification, where you are given a graph and you have to assign a label to each node. Link prediction, where you have a graph and you receive as input two nodes, and you need to output the probability that there should be an edge between those two nodes. And then the graph classification task, which you're given multiple graphs in input, and you have to assign a label to each graph. And if you think about it, these three tasks actually encompass a lot of real world applications of graphs. But if you look at the literature, you will also find many other use cases for graph embeddings. These are just the most popular, and that are used in things such as recommendation system, social network analysis, community detection, and so on. We have two main scenarios we are interested in. The first is the transductive one, where we have a single graph and we have the labels of a few nodes. And given the labels of these few nodes, we want to infer the label of the remaining nodes. Then we have the inductive task, where we have multiple graphs, and we might have all the labels for the nodes of a graph, or we might even have just some of the labels of the nodes in a graph, and we want to actually generalize to unseen graphs. So the inductive scenario is clearly much more complicated. So let's give a very brief look at some past approaches. The very first approaches were just based on that dimensionality reduction. So the most basic thing you can think of is you take the adjacency matrix and you perform PCA in order to reduce its dimensionality. Then some more advanced techniques that we proposed, and these are trying to exploit the graph structure, because of course when you do PCA you actually not caring at all of the graph structure, but since you have it, you should try to use it. So this is what other techniques are used. As I said, I'll just quickly go past, but if you're interested, feel free to ask me for more information. Then in around 2014, when skipgram was proposed for natural language processing, people started applying this idea also to the graph domain. And so what we have is that we consider a random walk as a phrase, and each node in the traversed by the random walk is a word in the phrase. So if we perform a lot of random walks, then we are actually creating a corpus of sentences. And once we have a corpus of sentences, then we can just use the scriptgram model and obtain our embeddings. And in fact, these were one of the first methods that enabled the use of deep learning on graphs. Nowadays, they are not state of the art. State of the art is given by graph neural networks, but they are still fairly decent models. And especially if you don't have node features, then using random walk approaches is still a viable solution. And successively, other, let's say, refinements of the skipgram approach have been proposed, such as node-to-back and planetoid, and things are started to get more interesting. However, right after this, however, the graph neural networks have arrived, and these have literally revolutionized the field and are now, as I said earlier, one of the hot topics of the deep learning community. So I will start by presenting what is the message passing framework, as a lot of graph neural network models can be seen as an instantiation of this framework. So first, let me start by defining the matrix H as the matrix that will contain the node embeddings. So the ith row of the matrix H will be the node embedding for the ith node. And at the beginning, at iteration 0, or at layer 0, we will have that the embedding of each node is equal to its feature vector. And so in the message passing framework, we have that at each layer of the network, 3 operations are performed. First of all, messages are created. So for each edge ij in the network, a message is created using this function message, which could be literally anything you want, but usually, of course, it is a neural network. And it is a neural network that takes as input the representation of the node embedding of the ith node, the node embedding of the jth node, and if you have them, also the features of the edge. Uh, Once we have a message for each edge, then we have that each node aggregates the messages from its neighbors. So, and here, one important thing to remember is that the aggregation function must be permutation invariant. Otherwise, we would have that by changing the ordering of the nodes or of the neighbors, we would obtain a different result, which is clearly something we don't want. So the aggregation function is usually either a sum or an average, but yeah, it can be anything as long as it is permutation invariant. Finally, once each node has aggregated the messages from its neighbors, it then updates its representation. And this is done by a function that receives as input the aggregated messages from its neighbors and its previous representation, or its representation at the previous layer. And so for each layer, we have that these two operations are performed for each node, as shown in the figure here, and then a nonlinearity is applied, just like you would do in a multi-layer perceptron. So here in the figure, we have our rectifier linear unit, but of course, it can be your favorite activation function. And now, if you think about it for a second, then you will notice that after k layers of message passing, the representation of each node will have received information from all the nodes that are within its k-hop neighborhood. And with k-hop neighborhood, I mean the set of nodes that it is within distance k of the node. Let's now move on to graph convolutional networks. These models are by far the most popular instantiation of graph neural networks, and they are based on the idea of generalizing convolutional neural networks to the graph domain. This is in fact a very challenging task, as graph convolutional networks usually are applied on grid structured data, which has a very irregular structure, but graphs are actually very hard, as you might have different neighborhood sizes and various irregularities in the structure. And the most popular model in this category is this one, is the graph convolutional network, also called GCN, which was proposed in 2017 by Kipf et al. And this is a very, very popular model. And in fact, I would go as far as saying that this is the model that actually started all the hype around graph neural networks, as it is extremely fast at inference time, and it achieves results that are much better than what was previously possible with the methods that were available at that time. Now, this is the formulation of the model. So at the beginning, we have that the matrix H, the one containing the node vector embeddings, is said to be the feature matrix as before. And then this is the propagation rule. I think this is quite, it's not a difficult formulation, but it can be a bit challenging at first. So I will try to explain it by looking at what happens at the node level. Consider this very simple graph. Then we will have that the embedding of the node 1, which is the red node in this simple graph, at the next layer will be given by a weighted sum of its neighbors. And as you can see here, we are considering the adjacency matrix with added self loops. So V1 is a neighbor of itself. So this is a weighted sum of the neighbors of V1, and where the weights are given by a very simple multiplication of the square root of the degrees. And this final vector is then multiplied by a learnable matrix. So W is what you will learn in doing stochastic gradient descent, so during the training of the network. And then, as always, a nonlinear function is applied. For example, the most popular that I think we all know is the rectifier linear unit, but of course, any nonlinear function can be used. And if you are a fan uh, of graph spectral theory, this model has some very nice properties that you can go check out. And now, if you understood how it works at the node level, then you can see how this formula is actually performing this operation for every node in parallel by simply doing a few matrix multiplications. And uh, this is why this model is extremely fast, as on especially on GPUs, matrix multiplications are very, very fast. GraphSage is another very popular model, and this is based on a different idea. GraphSage was created with the idea of having an inductive model, so a model that can be used on unseen graphs. So here the idea is I'm going to learn some aggregation functions. So I'm going to learn some functions that receive as input a set of nodes and give me as output a vector embedding. And so once I have learned this function, I can actually use them on any graph I want. It doesn't have to be the one it has been trained on. And I think the pseudocode is very clear. We can see that at line 1, the initial embedding of each node is assigned to be its feature vector, as always. Then we have that k is the layer of the network, so bit k is the total number of layers we want. And we have that at each layer, for every node, you aggregate the embeddings of the neighbor of its neighbors, where aggregate can be any function you want, and again, it has to be permutation invariant. Once you have this aggregation of the nodes, you then concatenate it with the embedding of the node at the previous layer. You multiply it through a learnable matrix, so this is learned during gradient descent, and you apply a nonlinearity. Now, so the only thing you're learning here is the aggregate and this, if it is learnable, because it can also simply be a sum or a mean operation, and this weight matrix W. So you can actually apply this on any unseen graph. I then added this slide just as a curiosity, because even if the field of graph neural networks is relatively young, like as you've seen, it started in 2017, these models work so well that they are already used in production systems by a lot of big companies. And a real emblematic case is that of Twitter, which in 2019 acquired a startup called Fabula AI, which was led by Michael Bronstein. And this startup was based on graph neural networks for fake news detection. And now Twitter has a whole team basically just doing research on graph neural networks. And yeah, so this is it for the part on graph neural networks. And of course, there is much more to say than what I have presented here. So if you are interested in learning more, then feel free to contact me and I will be happy to help you. We can now move on to presenting the paper Infusing Knowledge into the Textual Entailment Task using Graph Convolutional Networks, proposed by Kapanipathy and others, and that was published at AAAI 2020. I will start by presenting what is the textual entailment task. So the input we have is a couple of sentences, a couple of texts, where the first is usually called either text or premise, and the second one is the hypothesis. Then the output of the model is one of these three possibilities. Either if there is positive entailment, which means that the hypothesis can be proven by the premise, if there is neutral entailment, which means that the premise says nothing about the truthfulness of the hypothesis, or negative entailment, which means that the premise contradicts the hypothesis. So as an example of a premise, we have Marita and Jay both were at the scene of the car crash. And as an example of hypothesis, we have that multiple people saw the accident. So this is an example of positive entailment, as the hypothesis can be proven by the premise. And if you think about it for a second, this is a very hard task for a computer, because while if we read this, then for us humans, it is automatic to say this is a positive entailment. This is actually a very, very hard task for a computer, because, for example, it has to it has to understand that accident refers to car crash. It has to understand what multiple people means. It has to understand that Marita and Jade are persons. And if you just look at the words, for example, the only word that is both in the hypothesis and in the text is the, which is a very common word. And so for computers, this is a really, really hard task. And if you want to play around, there is this website that you can check out, and you can select a model. Of course, unfortunately, there's not the model presented in this paper, but there are other three models. And you can insert whichever premise and whichever hypothesis you want, and you can see what the models output, and it's quite nice. Let's now dive into the method that the authors propose. They call it KES, which stands for Knowledge Graph Augmented Entailment System. And it is a model that can actually be used to enhance any existing natural language inference model. And natural language inference is another way to call the textual entailment task. So we will see, I will first present how it generally works, and then we will go over each section separately. So the input is the premise and hypothesis text, of course, which are given to a word embedding model, such as Word2Vec or BERT. And these will produce some text embeddings. So for example, for the premise, we have P1 to Pn, where P1 is the embedding of the first word in the premise, and Pn is the embedding for the last word in the premise, and so on. And then these text embeddings are given to a standard text model and to a module that reasons over a knowledge base. So the standard text model would just process the text and give a final global embedding of all the text. So it's like, in a certain way, it's like if it's summarizing the content of both a premise and hypothesis. While the second module, which is the one reasoning over the knowledge base, is actually taking as input also a knowledge base. It is then using the premise and the hypothesis to extract a relevant subgraph, and it is then using a graph neural network to encode it into a fixed size vector. Then these two final encodings are passed to a final classifier, which, for example, can be a multi-layer perception, and the output is given. So the output is either positive, neutral, or negative entailment. So let's now focus on what is the standard text-based model. Because in the paper, the authors do not specify any of this, as in fact, their proposed method can work with any existing model. So they just use some NLI model available from literature, but just to have one in mind, I wrote here a very, very simple one. Like, I don't expect this to work very well, but it's just to have something in mind. So imagine having a multi-layer perception, or just a neural network with multiple layers, and that takes as input the concatenation of the word embeddings of the premise and the hypothesis, and then processes it to a series of layers and outputs if there is positive, neutral, negative entailment. Then we will train this system this way, and we will then not be interested in its prediction, just like we do with Word2Vec, but we will be interested in the representation at the last layer, which is a lower dimensionality representation that actually encodes all the information coming from premise and hypothesis. Let's now focus on the knowledge base. As a knowledge base, they use ConceptNet, and I just took this description from the website. ConceptNet is a freely available semantic network designed to help computers understand the meanings of words that people use. And here it is there's the link to the website, so you can go and check it out, and you can actually explore the knowledge base. But anyway, if you're not familiar with what a knowledge base is, it's simply a graph where each node represents either an entity or a verb or like something of interest. And then each edge represents a relation between two entities. And so each edge has a relation type. So different edges mean different things. Now we will focus on the core of the method that the authors propose, which is the part that reasons over the knowledge base. I summarized here the steps that they do to obtain the final representation for the reasoning operation. So first, they map the terms in the premise and the hypothesis text to concepts in the knowledge base by performing a max substring match. And let us call S the set of these mapped nodes in the knowledge graph. Now we expand the subgraph induced by S to include one-hop neighbors. And we then perform a filtering based on personalized page rank. So personalized page rank, if you don't know it, it's a type of random walk with restart that assigns a score to each node. And this score indicates what is the probability of ending up in a or passing through a node while performing a given random walk with restart. In particular, in personalized page rank, we have that it is personalized, which means that the restart is biased towards the nodes in S. And what they do is once they have performed this, they have obtained the personalized page rank scores, then they just exclude all the nodes that have a score which is lower than theta, which is just a hyperparameter. They then take this filtered subgraph and they add self loops and they create a premise and a hypothesis supernode. For example, the premise supernode is just a new node which is connected to all the elements to all the nodes in S, which have been mapped from words in the premise. And the same thing is done for the hypothesis supernode. Then everything is encoded with an RGCN. This is how they present it, but I think this formulation can be a bit clearer. So imagine having a different GCN per each relation. And so you ran all these GCNs in parallel, which means that you will obtain a node embedding for each node, for each relation. You then sum them all together. And so you have that the embedding of each node will be influenced by the embeddings given by all the relations that that node takes part in. Once we have this node embedding for each node, we then obtain a graph embedding, which is obtained just by multiplying each node to a learnable matrix W, and then summing everything together and applying a nonlinearity again. Finally, the final output of this module is the concatenation of this global embedding vector and of the embeddings of the two supernodes that we defined in step 4. So if we look at the figure, which is a graphical way that is present in the paper to explain this concept, we can see that premise and hypothesis are mapped to concept in ConceptNet. Then, and this is the resulting subgraph. Then the one-hop neighbors are added, and filtering based on the personalized PageRank score is applied. Finally, for each relation, we have a different GCN that produces a node embedding for each node. The embeddings for the different relationships relations that a node takes part in are summed together. Nonlinearity is applied, and here we obtain the final vector, which is then passed to the classification layer together with the output of the standard text-based model. We pass now to the results, and we can see, so these are existing models where that are based only on text. So they perform the textual entailment task just by looking at text. And this is the result and these are different data sets for natural language inference or textual entailment. And this is what the result that is obtained once key ES is added to them. So as we can see in this first 3 data sets, there is not that much of an improvement. However, the authors specify that it has been shown in literature that in these 3 data sets, there is a lot of bias, which makes the text very significant. Like it's very easy to infer the entailment based on the text. However, in the breaking NLI dataset, this bias has been greatly reduced. And in fact, we can see that the performance of the models that just look at text are not that high. And we can see that key S is actually significantly increasing the performance of these models. On this second table here, we can see they provide the average number of nodes and edges which are added after the PPR filtering. And this is just to show that the key S is actually going to access information that is not available if you simply look at the nodes given by the max substring matching. So it is actually extracting more information than what you can obtain from the max substring matching. So this is it. I hope everything was clear, and I'll see you all on Monday to discuss this paper.